So lecture series on module theory is the second lecture. The lecture on basic idea of module. In first lecture we deal with ring. It's the overview of ring. Now we go with this module, a fundamental idea of module. So we start with left module. So what is left module? So left module, there is a ring R. R is a ring, and it may or may not have one. That identity may or may not have in this ring. But some author in some books they taken as this one is there. So there are two type of definition. In some authors, some books, they're written that okay, this if one may or may not be there in ring. If one is in the ring, then we they call it is unitary module. So if it's one may or may not be there, if one is there, say unitary module. Some book or some author they take that okay, this module means it's one is there in ring. So you have to first check whether which definition is taken in that book. When you read a book, you should check whether is one is taken as a taken granted that one is there or not. So in our lecture we just take okay, one may or may not be there, or may or may not be commutative. That is always true, that every author take okay, may or may not be commutative. But one, this is a slightly confusion. In some book they take one is there, and some book the author take okay, one may or may not be there. So now what is left module? Left R module M is the abelian group. This first of all it must be abelian group. So it's a group. So there, if there are two elements x and y in M, then x plus y in M, x plus is the binary operation, and then there is a 0, x plus 0 equal to 0, x plus y equal to y plus x, and then the associative property x plus y plus z is x plus y plus z. So this is a group, and there is a scalar multiplication. This group has a scalar multiplication. In a group there is only addition between two element of M. Now there is scalar multiplication. What is the scalar multiplication? Scalar multiplication basically is the element from R and take an element from N. So it is a element of R cross M. So it is an element of say x comma a comma x in R, and say x in a in R and x in M. So it's a modular element. So like a vector space. In vector space, we same thing. So in vector space, we instead of ring R, we take a field, and instead of a module, we take a vector space. So we take a vector, that is x is a vector from that vector space, and a is the element of the ring or field that we say is a scalar. Same synonymous. It is scalar means the element of the ring. Scalar means the element of the ring. So what is scalar multiplication? R cross M, element of R cross M to M. So if you take two elements x, a and x, a from ring and m x from M, that ax in M, ax in M, and such that the three property, this is the one property is distributive from the left. So it is x and y from the element of M, and a from R, and then other right side thing. So a plus b now in A R, and x is M. So same thing. And now is a sort of associative, is not associative because a b are in R and x is M, so sort of associative, a into bx. So a bx equal to a into bx. These three condition hold, is assumed to be hold. Now in some author they take fourth one, say like that. So a one, if one is there, then 1 into x is x for all x. So some author take the fourth condition, who take that one is there. And if in our lecture we take okay, one may not be there. If one is there, then it is called unitary ring, and in that unitary module, sorry. So in unitary module, 1 into x is x. So in some author, unitary module, in other books, the unitary module actually means module, and some book take module as a more general term, may or may not be one. By the way, in everywhere is no commutative or may not be commutative. That is true for every book. For every, they all author take that commutative may or may not be there. Now for left model, there is some very simple result is something like vector space also there, in ring also there, you know, if 0 into x equal to a into 0 equal to 0 for all a belongs to R and x belongs to 1. Remember this 0, that 0 into x, it's a left module, so this x is from M and this 0 is actually in R. Now when we write a into 0, clearly it is, it's note that so it is 0. Now this 0 is in M and this 0 in R. When I write this a into 0, then this a in from R, a in R and this 0 in M. So that means this 0 and this 0 are the same, but this 0 is a different. In book they write something like that, a 0 R into x is equal to a into 0 in M or to 0 into 0 in M. But I'm not writing in this that too much. Otherwise, the notation will be very, there are several notations. Actually, these zeros are different, but this is clear from the context. Once I write 0 into x and I write a into 0, it is clear that these two 0 are different. So like 0 in the real number, 0 in the null vector, 0 in 0 matrix or null matrix, or 0 in the complex number. They are all different type of 0, but we take the same notation. Otherwise, there will be several notation. It's just boom of notation there. So to avoid this such a huge notations, we use the same notation for the different element. But still, by the from the context, it is clear which notation actually by. Something like in literature, one word has different meaning. The same word, single word has 10 different meanings, say. And this meaning is actually, we know what is the meaning of this word in this sentence. So it is clear from the context, from the sentence. So similarly, it is what is a 0, which 0 is this, is clear from the context. Remember again, these three zeros are the different. The last two are equal and this is different. So you can easily prove that in like vector space proof, or in it is easy homework. And from in ring also there is, we know 0 into a equal to 0, so same proof. Similar proof in ring also there, in minus ax equal to minus a into x is equal to a into minus x for all a belongs to R and xy belongs to M. Here just x belongs to M, so it's not no y. So it is again, it is the proof is very easy. In any ring, in ring theory, you know how to prove this. There is one more result is mn into x. This a is from R, this x is from M, and this m or n are integer. So one thing, how do you define some? If m is integer, how do you define ma? Ma is nothing but sorry, not it is an integer. So if m is natural number, we define ma like that: a plus a plus a plus a m times. So we add a m times. This is the ma. So 2a means it is 2 in 2, not 2 into a. Remember that 2 may not be in the ring. So 2 may not be in the ring. Ring may be considered of say cow, dog, and something like that. So a set of animals. And module maybe consist of this say West Bengal, Bihar. So it is like cow into West Bengal. So 2 cow is not actually some 2 into cow. It is 2 cow means cow plus cow. 2 into West Bengal means West Bengal plus West Bengal. So because 2 is not in the ring, it is not. But cow into West Bengal means it is just cow from the ring and West Bengal from the module. So cow into West Bengal is defined. But 2 into West Bengal is not defined because 2 is not from the ring. So 2 into West Bengal means West Bengal plus West Bengal. So it is like that. So by definition, 0 into a we define as a 0. So again, this 0 is our 0. This integer 0. This 0 in integer. This 0. So here our 0 from class 2 or 3, that 0. But this 0 is not the same because this is element of M. Remember, this is element of A. If a is in R, then it is just in R. Again, 0 into x, if this 0 in Z is the integer, our class school 0, that school level 0, and that this x in M. So that is 0. So this 0 is actually in M. So again, so if I write 0 into x, you have to be clear about that, whether this is x is from M. Now whether this 0 is from the ring or is 0 is actually our 0. So actually it's the same thing. It is 0 is from our ring 0, then it is just 0 in M. And if it's the 0 in it's our 0, our in school level 0, this also in 0. Remember, this to 0 is same, but this to 0 are different. It's a ring element. This 0 may be a, say, dog into some West Bengal equal to West Bengal, or maybe Bihar is an identity element of the module. But this 0 into West Bengal is just Bihar, like that. So M or N are, by the way, this is a for natural number. For 0, you define this, and for negative number, for if N is, say, natural number, and if we multiply it with a negative integer with a or M, we define like that. It is just minus a plus minus a plus minus a. So minus a is defined. Minus a is just the inverse, that is additive inverse of a. Minus a is not minus 1 into a. Actually is minus 1 into a. It's by the second property is actually minus 1 into a, but minus a is actually by definition is just additive inverse of a. So it is just n times. This is the definition. So you can easily prove that M into a Mn equal to into a ax equal to Mn x, and a into Mn x, Ma into Nx, and Na into Mx, whatever. So these are several things, and you can easily prove that these are all equal. So next, some definitions. So zero module about R. So zero module is just single element. M contains a single element. Just only one element are there. 0 is there. The only one element is, because since it's a group, that 0 must be there. At least one element must be there. So identity must be there. So this 0 is actually not our school 0. It is just 0 in the element of the module. Now, by definition, a into 0 is 0. So every scalar multiplication gives 0 because there is only one element in it. Similarly, we can define right module. So this definition of right module is again same as a left module. The right module will be same. So it is like M cross R. So it is from M cross R to M. And this X is from M, and A is from now R. So this goes to XA. This goes to XA. And again, these are all thing is same. So it is x plus y a equal to xa plus ya. Remember, now x and y is coming from the module and a is coming from the ring. Similar thing happened with the 2 and 3, and for 4 it is just x into 1 equal to 1 if it is a unitary right module. So right module is same definition like left module, and we can talking about this propositions also for the right module. The same proposition is just the ring element will be from the right hand side. Now there is this definition, the unitary left or right module. So unitary left module means it is R has 1, and this a 1 into x equal to x for all x. And similarly for unitary right module, it is just x into 1 equal to x for all x. So this is some basic definitions. Now example. So there some examples are there. So any vector space. So any vector space is a module. So because vector space over a field. So vector space over a field means field is a ring. So every field is a ring. So vector space, and we know this all 4 properties of the vector space. Basically, vector space is a unitary module. Because this ring with identity, and all 4 conditions are held. Distributive from left and right, 1, associativity, sort of associativity, and 1 into x. These 4 are there for vector space, and rest are everything is okay because this is a field, so it is a ring. So there is in vector space there is a abelian group. Vector space is a set of all vectors with a vector addition is abelian group. So it's a module. So what is the extra thing? Extra thing is this ring is now a field. It's much more thing is there. So inverse of my multiplicative inverse is there, and commutativity also there. So the vector, there are two sets. One is the ring, which is now filled, and other is the module set, which is actually the vector space. Now, any abelian group. Now, any abelian group is actually a module. Why any abelian group is a module? Because you can take this ring as a Z. If you take ring as a Z, now you can construct a module, any group. So G is a group. G is abelian group because that abelian is important for the module. So G is the abelian group, and we want to find we want to make this as a module. So we need a ring. So we have a ring. Z is a ring. Z with addition and small multiplication, usual multiplication. This Z is in our school level Z integer. Z addition in plus and dot. Now, how to define this scalar multiplication? So scalar multiplication, if it's a left module, we have to define like from the left Z cross G to G. So how do you define Z cross G to G? This definition is just natural way. So take an element from N from Z, and element G from G. How to define N into G? Again, it's clear. So if N is natural number, we define G plus G plus G n times. N times. Again, if it is 0, we define it like a 0. 0 is the 0 in G. Again, this left hand side 0 is means our school 0, and this right hand side 0 is our that 0 of the group element. Now, and for n is negative integer minus n. So in that case, we define it's like minus G plus minus G plus minus G n times. N times. So this is the definition, and by this using definition, you can easily show that is all four properties that four properties of this module, the scalar multiplication is trivial to check that four properties are satisfied with this definition. Next to the polynomial ring, you know that is very important ring. So if R is a ring, and this Rx is called the polynomial ring, this set of all polynomials, like a0 plus a1x plus dot 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 a n x to the power n, and this plus is not actually, this is not a plus, is actually the formal notation. Formal is called formal addition, is not actually 1 plus x is not actually 1 plus x, it is actually 1 comma 1. So it is just polynomial ring, and any polynomial ring is actually a module over that ring, that R. So the coefficient actually coming from the ring. For a polynomial, the coefficient coming from the ring. Now this polynomial R is a ring, and this Rx, the set of all polynomials against a ring, is another ring. Now this Rx can be from module over this R. So Rx itself is a ring, and Rx is also a module over R. How Rx is a module over R? Similar way, you just multiply this addition of two polynomial is okay. Only scalar multiplication you have to define, but it's a trivial way to define. So any element from Rx, if you take any element, say polynomial is fx, and if you take a element in R, by definition this a into fx is clear. It is just a multiplied with this fx. So if fx is say it is a0 plus a1x up to dot a n x to the power n, n is some natural number. This is just a into a0 plus a into a1x, and this is defined. This is defined because this a and a1 and a0 all in ring. So in ring, this addition is, the multiplication is defined. So that's why this is a module, and you can easily check that all these conditions, the associativity, distributive, sort of associative and distributive, is true, and 1 into x is x, 1 into fx is fx. Clear. Now, one interesting example is this ring itself is a module over ring, that ring, like a vector space, like a field. F is a vector space over F, is one dimensional vector space over F. So a field itself is a vector space over that itself, that F. Similarly, R, if R is a ring, that R is a module over that ring. and the definition is clear. The scalar multiplication is clear. Just take R to R. This R is this R is from, this is the like a ring structure, and this is a module. Same ring, same set. So now this R cross R is defined easily. It's just AX is this AX in ring and X is from the module. So AX is just a scalar multiplication. That's a ring multiplication. So this scalar multiplication, that's just a ring multiplication. Similar for the right module. Same thing will occur. So like F is a vector space over F. This is a ring itself is a module over ring. That ring. Now submodule. Submodule is very important. If N is a non-empty subset of M, is a submodule. Any subset like a subgroup is submodule if first of all N must be additive subgroup of M, and N is closed under the scalar multiplication. So it must be like a subgroup. It must be a subgroup of M, and N is closed. Now, so N is a subset of M. Now, if you take a element from ring and a element from N, if it is element from N, that must be element from M also. Now, AX is M. That is because M is module, but AX may not be in N. Now, if AX is in M, then we say it is submodule. Sorry, it's N. Then we say it is submodule. So submodule have two conditions. It is like a subspace. The addition and this scalar multiplication is in this ring, is closed. Now, again, some easy example is if S is a subring, then R is a left or right module of S module. So S is a subring of R. So you can take that R as a module over that subring. It's easy, because if you take element from R, now R work like a acting like the module. Now S is acting like the ring. So element of module and ring and module is now element of the module. So because in the element of R and element of S is the product, the multiplication is the element of R. May not be element of S, but element of R, because R is a ring. Though it is just a so it is a module, but the other way is not true. If this R is S is submodule of R, then S may not be a R module. But if S is an ideal, if it's a left ideal, then S is the R module, because we know if you take a element of S and if you take element of R, the product is now in S, because S is a ideal. So if it's ideal, now S is a R module. And examples are very clear examples: subspace of the vector space and subgroup of the abelian groups. These are all submodule. Now the last important thing is homomorphism. You know what is homomorphism? It is just a structure preserving map. So any if M1 are two module, so homomorphism of the left module, similarly for the right module, is on M and N. There are two conditions, like is it like a linear transformation, like in the vector space. So f of x plus y equal to fx plus y, just a structure preserving. So since there are two operations, plus and scalar multiplication, we need define this f for two different operations. F of x plus y equal to fx plus fy for all x and y, and this f of ax. Now a is in R, x is in M, is just a into fx. It's just a linear map. This vector space is just a linear map. And for the right module, x from the right side. So f of ax equal to x equal to fx into a. And what is monomorphism? Every injective homomorphism is called monomorphism. Every surjective homomorphism is called epimorphism. And the bijective homomorphism is called the isomorphism. This monomorphism and epimorphism both. What is endomorphism? Endomorphism, if M or N are equal, then it's called endomorphism. Any function from module M to M is called endomorphism in M. And what is automorphism? If this M and M are isomorphism, this is if it is isomorphism, then it is called automorphism. So automorphism means isomorphism as well as both the domain and codomain set are same model. So it's called automorphism. So these are some names, some terminology in homomorphism. So in this lecture, up to this, next lecture we will discuss on the different properties of homomorphism and different isomorphism theorem. So This is the end of lecture 2. That one more reference is N.S. Gopal Krishnan, University Algebra.